Okay.
Okay, I'm going to start sharing the screen. Okay, you should be able to see my screen.
Yeah.
Okay, awesome. Yeah, thank you so much for the invitation. My name is Alexander Rodriguez, along with Harsha Karmati and Professor Aditya Prakash. We are from the College of Computing at Georgia Tech, and we are going to be presenting this workshop titled Data-Driven Computational Epidemic Forecasting. Please let me know if there is any problem with the audio. I think it's okay, right? So far, right? So we are coming from Georgia Tech. Our lab is called Aditya Lab. One of our focus is exploring the performance of data-driven models in epidemiology and public health, specifically surveillance, interventions, and vaccination. So for here, we recognize that there are some data from multiple sources that is often more sensitive to what's happening on the ground for the epidemics. And we can provide with these data-driven models a complementary, helpful perspective to traditional methods. So now a bit about us. The PI for the lab is Aditya Prakash. He's an associate professor. He got his PhD from Carnegie Mellon University. He is interested in data mining and applied machine learning for network sequences with applications to the epidemiology, public health, urban computing, the web, and security. Thank you. So I am Alexander Rodriguez. I am a fourth-year PhD student graduating in May 2023. My interests are in data science, machine learning, time series, and networks, usually motivated for critical infrastructure network problems or epidemic forecasting. And also Harsha Karmati, he is a second-year PhD student. He is interested in epidemic forecasting, probabilistic forecasting, and uncertainty quantification, and in probabilistic models. So we have created a workshop website for you all so that you can have all the resources that we are going to be sharing. I'm going to post it also in the chat. Here's the chat. Sorry for that. Oh. So this is the website also. It is also on the chat and here also on the slide also. As it says there, we will post all the slides and also the talk of the videos there. So the outline of this talk, we're going to be looking at the epidemic forecasting, some of the concepts that are common there in order to understand the setup for these problems. We are going to go now, after that into the methods, mechanistic methods, statistical methods, in which we are going to put a lot of emphasis because this is a data-driven focus, and also some on the more novel hybrid methods. Then we are going to move to the ensembles, and we are going to talk about epidemic forecasting in practice. We will have 15-minute breaks after part 2 and also after part 3, and will be available for questions if you have some questions for discussion. And feel free to, if you have some maybe quick questions or clarification questions, feel free to interrupt us to unmute yourself and let us know what is your query. So the plan for the workshop today, we're going to talk about theory and research in epidemic forecasting. We're going to first set up the epidemic forecasting problem, talk about some key concepts and models in epidemiology, and then move to statistical modeling and deep learning, in which we're going to focus on research innovations, and also how you can, and later we're going to talk about some experiences in real-time forecasting that we had in the US, some coding examples with mechanistic models and statistical models, and a demo session where we are going to explore how to use available resources online to make statistical corrections to our forecast. So as I mentioned before, the workshop focus is going to be in computational data-driven models. So we're going to be spending most of the time on from that perspective, on that material related to that. And we are going to also focus on short-term forecasting up to 4 weeks ahead. So let me introduce maybe just very briefly we, in forecasting infectious diseases, we do this because we want to inform resource allocation, inform policy, improve preparedness. And as a background, we have the traditional methods that are based on ODEs or agent-based models. We are going to see them in this in today's workshop. They are well established. They are usually often used in general epidemiology. And on the other hand, we have the data collection has increased. And the problematic is that these methods have difficulties ingesting these data sources. And I want to explain you with an example why it is important to pay attention to the data sources. You can see here an epidemic curve where we have in the x-axis, we have time. In this case, it's a week. And in the y-axis, we have the number of deaths that we have for each week. So we are in at this time where we have a line. Sorry, I'm going to just put the laser point. Here we are at this time. We can think about possible near futures, like maybe the epidemic curve is going to go down, or it's going to stay still, or it's going to go up. And in my opinion, this looks like it's will go down. But actually, in reality, it went down just a little bit and then went up. And this complex behavior, we can only understand it when we are looking at other indicators. We are looking at the current number of infections, the interventions in place, the contact patterns, exposure to the disease of the population, etc. And this is many of these indicators, we can get them from data. So let me now, given this, why computational data-driven forecasting? We have that the epidemic spreads is a spatiotemporal phenomenon over multi-scale networks. There are new end-to-end methods, usually coming from machine learning, that are available and capable of modeling data with minimal assumptions. And we have been, under these reasons, we have been exploring before and after the COVID-19, the performance and utility of these data-driven models in short-term forecasting. And in our experience, we have been seeing that they have been performing very well. We have been using them in influenza forecasting for the last few years, and also during the times of COVID, at the beginning of times of COVID. We have been using it for COVID mortality, weekly COVID mortality, and also daily COVID hospitalizations. And we have found that these models perform well. Our deep learning model is the top 5 model in the CDC-led evaluation. There is a paper available online that has this evaluation, and we have been put in this ranking also. And we have this our model also, our predictions have been shown or showcased on the media. We have been awarded in some data science challenges, the first organized by Facebook and Carnegie Mellon, and also C3AI. In general, also this has been, for a data lab, has been part of our response. We have been also working other areas, like for example, visualizing non-pharmaceutical interventions, using on-campus mobility logs in order to inform interventions, and other, if you are interested, please visit the website that is on the top. And we have had, and this work has allowed us to get several publications, recent publications regarding to both influenza, COVID, and also even hospital-acquired infections. And coming soon, another publication that we will release is a survey paper. It's a preprint in this case. So we are working on a survey paper for data-driven computational epidemic forecasting. So many of the workshop material for today is based on this survey. We are going to release the preprint on archive, and we will actually post this preprint link in the workshop website. So please stay tuned. So now I'm going to start with epidemic forecasting. So here we have a depiction of the pipeline of how this can be represented. We have first the data processing, then we have model training and validation, and then we have utilization and decision making. In data processing, we have multiple sources coming from companies, institutions like CDC, And these data sets usually often have some data quality issues like maybe delays, anomalies, and revisions. We have to explore them, analyze them, clean the data. That's one part of the problem. The other part is understanding what we want to predict, how they are going to be related to decision making, and how much in the future we want to predict also. That is also part of the problem setup. Later, we want to go to the model training and evaluation. We have made several considerations. Here, for example, we have listed some multi-scale dynamics. We want to, because the predictions are going to be used for decision making, we want them to have appropriate and certain notification. And all these considerations are going to enter to the modeling stage, where we may have neural models, we may have mechanistic models, hybrids, ensembles. We are going to do some calibration, training. We're going to also validate the model and select them. And later, we're going to, once we are confident about our predictions, we can use them for maybe putting them in a dashboard so that they can inform to the public, can participate in some initiatives hosted by public health institutions. And also in our case, we have been submitting it to be part of an ensemble of many other models, including mechanistic and other hybrid models. And they are going to be finally being used for decision making, resource allocation, even personal risk assessment, and so on. So we want to focus in this the first part in understanding what are the epidemic forecasting, the elements of the epidemic forecasting setting. So the first one is epidemic forecasting tasks, then targets of interest, spatial and temporal scales, the data sets that are available, and the model evaluation. And the first one, the common forecasting tasks that that are being used in this space are often, for example, what are the future incidents? What are the next 4 values? This is usually the common period or the common window that we want to predict. What are the 4 values in this epidemic curve? The second task may be peak intensity. So we may have that, what if we know that there's going to be a seasonal epidemic curve, we may know that we want to know how much is going to be the maximum value of this curve, how much or when this is going to be, when it's going to happen. And in the case of the onset, it is the point where after 3 consecutive weeks, the epidemic values have been above certain threshold. So this is usually referred as the start of the epidemic season. And this also is of interest for decision makers. So I want to just maybe briefly say that for COVID-19, at least in the US, the focus has been in future incidence prediction. And this is because the peak intensity at peak time, even the definition of peaks is sometimes not clear. There are some difficulties in defining the peaks, and also it is also not very well understood how this can inform decision makers when we have maybe multiple peaks even in a very short period of time. So that's why probably some of the reasons why it hasn't been explored yet in COVID-19, but it has the focus has been usually future incidence prediction. Now, regarding to the targets of interest, so this means that what is the metric or indicator of the epidemic spread that we want to predict? Regarding to influenza, the commonly it has been used in the US and also internationally is percentage ILI. Here, this is a symptomatic metric, so it means that it's counting how many outpatients or patients going to the hospital have symptoms related to influenza-like illnesses. And this is a syndromic surveillance metric, so it means that it is not yet a lab test, so it is basically purely on symptoms. And because of this, it has some interesting properties that it can be widely available in many states and in many regions. But also one of the drawbacks is that there may be some other diseases that are also have some symptomatic similarities, and they are being counted also as ILA or an influenza. A more reliable but scarce metric is lab test hospitalizations. That also has been explored by CDC. CDC has some prediction initiatives, which we are going to talk more in detail later, but they have this target has been also explored there. Regarding to COVID-19, the common metrics has been mortality, hospitalizations, and cases. Now we have to also, once we have decided what to predict, we have to go to what spatial and temporal scale we want to predict this. So oftentimes the predictions are done at national and region, national level, and also region, state, or province. So here in the US, there are several regions you can see here. For example, region 4, they have eight states, this grouping 8 states. And this grouping is because each state, sometimes the data for each state is noisy, has some spikes. So when you aggregate several states, you have a more robust metric, which can be actually useful for informing public policy. That's why, at least in influenza, this has been usually the most common approach to use regional predictions. So that's why I put also here county and city level. Usually they are very, very less common, but definitely there is a need to move forward to it because we need more localized forecastings. So this is, I would say this is a an active research area, and there are definitely challenges in the data on how to do this. And regarding the temporal scales, we have we can predict on a weekly basis. That means that we are going to predict for each week one value, and also we may predict also for on a daily basis one value for each day, usually for 28 days, as I mentioned before, 4 weeks ahead. So we may have this usually from our experience. What has been preferred is the weekly temporal scale. So regarding to data sets, you may have seen this if you are familiar with epidemiology. The surveillance pyramid, we have any question? Okay. So we have general population at the bottom, and they have some people that are infected. Some of them are asymptomatic, and we move up, and the group is being reduced. Right? The group is only symptomatic, only some people that are seeking care, some people are hospitalized, some people are in intensive care, and then some people are deceased. So at each state of this pyramid, or at each level, we can get some information about what is happening. We can only get some samples. And additionally, we have been having this, what is called line list data sets. Line lists are records of who, when, and where a person was infected. And from here, we can derive, aggregate and derive metrics that are going to be useful for understanding the epidemic spread on a particular region. And this has been the traditional approach for many years. Now, with the advent of digital data, we have now digital epidemiology. And this pyramid that we had before can be now populated with many other data sources. For example, here we have mobility, contact tracing, satellite images, social media, and behavioral surveys, and so on. And of course, they are complementing also the traditional data sources that we had before, coming from usually CDC or other public health institutions. So let me linger a bit on these digital data sources. We have, for example, search engines and social media. There are some ad hoc search engines, for example, Google, Yahoo, that people have explored how to use them in order to understand the epidemic spread better, or have some information that can inform better. And specialized search engines, in this case, Wikipedia, people have explored specific websites of Wikipedia that are related to flu, that, for example, the search or the visit or the number of visitors can inform us of the epidemic activity also. Also, similarly in social media, in tweets, this requires more a bit more work because it requires some processing of natural language. We also want to talk about that, and also RAS feeds. Regarding to online surveys, there has been symptomatic surveys, whether you have some symptoms, you may fill up some kind of form and then submit it. Similarly, we have also some behavioral surveys that Facebook has been leading these efforts around the globe, asking, for example, if you are adopting mask wearing, if you are social distancing. Those are the information that we can use for understanding the likelihood of spread or transmission. On the other side, we have mobility. We may quantify, we use this in order to quantify patterns within and across communities. And often sources are mobile call records and mobile apps. We may also have satellite images, like, for example, how many cars are parked in a hospital. That can be also useful to understand the epidemic spread. So then the fifth element is model evaluation. So here we have a point forecast in which we are evaluating only one single value per forecast. So, and also we have probabilistic forecast, which is evaluating the probability distribution of the forecast. And usually the second one, as is probabilistic, it captures uncertainty and is often more useful for decision making because uncertainty is very important in this kind of high stake decisions. Regarding the evaluation of point forecast, if we consider that the residuals are the residuals, which are these lines, black lines, are defined as a difference between the ground truth value and the prediction, then we can derive this several evaluation metrics. For example, root mean square error, mean absolute value, mean absolute percentage error, and mean absolute percentage error. These are based on these residuals of or errors with respect to the ground truth. And regarding the evaluation of forecasts, when we have probabilities, a log score, what it uses is puts, you have to assign a probability to the ground truth outcome, and for which you have to put, you have to first bin the domain of the outcome. So for example, let's say that in influenza, we usually have that the domain is from 0 to 13. So you will have a small bins of each of with 0.1, and you will put some probability on each of them. And then what is going to be measured in this log score is how many probability your model allocated on the right bin, right? And that is one metric that has been used very often. More recently, the focus has been on coverage score, which measures calibration. For COVID-19, these metrics, WIS, has been used in the COVID Forecast Hub, the US COVID Forecast Hub. This is based on, first, let me maybe explain IS and then WIS. IS, this is for an alpha. An alpha is the percentile. For example, you may have a confidence interval at the 50% confidence, and it's going to be different from the 95% confidence, 95% confidence interval. So for each alpha, it can be 50%, it can be 95%. You will penalize how far your upper bound and lower bounds are from the actual value, and also how wide it was your forecasting forecasting interval, how wide this lower and upper bound are from each other, how far apart. And WIS, what it does is aggregates this IS metric, the interval score, across several alphas, across several this confidence interval, this percentile confidence intervals. So okay, once we have defined this, how do we choose these evaluation metrics? And this has to be based on this, on what decisions are going to be made by using this. So you should often, in this kind of decisions, we value uncertainty and calibration. That's why probabilistic evaluation metrics are often more desirable. In our experience, we have seen that the log score is the predominant for influenza forecasting. And this is often used because influenza are within some bounds, and then we can discretize, we can create these bins that I was talking about, which are needed for this metric. For COVID-19, because mortality cases and hospitalizations are unbounded, the log score is not appropriate. That's why this WIS metric was proposed. So maybe I would like to ask if there is any questions so far. I have seen, or I'm not sure if, okay. I think there is no other questions, so I can I continue with now going to the model. Oh, okay, there is a hand, I think. Oh, please go ahead, Amal.
Okay.
Yes.
Thank you for this first part of your presentation. Can we hear me well?
Yes, yes, yes. Thank you as well.
Oh, okay, thank you. So, what do you mean by calibration? Calibration.
Yeah, calibration means that the predictions that you're making over time, they have to be, if you're saying that you have a confidence, let me go back a bit. Let's say that this is a 95% confidence interval. So what this means is that your model estimates that 95% of the times the ground truth value or the actual value is going to be within these bounds. So you over time, if you make predictions as and then over time you can aggregate this, you will see how many times the actual value actually fell on your confidence interval. So maybe there are some cases where the actual value was over here, and other cases was over here, and then other cases it was inside of your confidence intervals, and then you will count how many times you were right and how many times you were wrong, and then you by taking just the average or the accuracy across time, then you will see if what you were saying, that is 95% of the time, you were saying 95% of the time is going to fall within this bound, you will see whether or not it happened, right? So that is the calibration that we are talking about. Is it clear, Amal? Okay. Yeah, hopefully this is clear. Thanks for the questions. If you have any questions, so
yes.
Amal? Yes. Oh yeah, I was
yes.
asking
okay,
if it is clear.
Oh, okay, here. Okay, thank you.
Yes. Okay.
When can we say that the calibration is okay?
Yeah, that's a very good question. Usually, what we see is that, for example, if we are saying 95, let me say this. Well, if we are saying 95% of the time it's going to fall within these bounds, and we count across time, and then we are going to get a value. If it is the closest to 95, this is okay. This is very good. Same we can do with 50% interval. Also, we want to approach the closest to 50%. That is what it is expected in calibration.
Okay, thank you.
Maybe I have a question on that one of calibration. Yeah. This is Mohamed speaking. Yes, so I just want to try to understand exactly how do you do calibration? Do you use the same values that you are having, or how do you do it technically?
Oh, okay, yeah, maybe I can, let me see if I can write here. Okay, yeah. Target.
So, sorry, excuse me.
Yes.
I want to assume there's going to be a separate session for the illustration of these methods, like the computation. Am I correct?
Yeah, this is actually, yeah, there are some people that can make a whole presentation about this. Yeah, I agree with you. Yes. Yeah, this is a very extensive area, but yeah, but I can maybe explain very briefly this part, this specific part. So, for example, let's say that we are predicting 1 week ahead, 1 week ahead. And then we have some prediction intervals, right? We're going to have that is maybe from 20 to 50 first. Then we're going to have from the next week, we're going to predict from 30 to 40, after 60, let's say. Then we're going to predict for 30 to 60 or 50 again. And then on each week, we're going to make this 1 week ahead prediction. And we will see for the after the week passes, we will see that there is a value, a ground truth value of what was the actual value of the epidemic. Let's say that here we had the value here. Here we have the value here. And here we have the value maybe here. Okay. So in this case, I didn't say that, but let's say that this is a 95% confidence interval. So within these 3 weeks, the values were in our confidence interval only one time. So we have 1/3. This is our calibration, 0.33% is our calibration score. And the actual value that we wanted, it was 95. So we are far away from that. So what we want to achieve is that this X has to be inside of the confidence intervals, and then our calibration score is going to improve, right? If you imagine that this X was inside, then it's going to be 66%, right? Or 67%. So yeah, the people usually, we don't usually take only 3 points. We usually take several points and also aggregate over 1 to 4 week aheads. But this is the basic idea on how to calculate these calibration scores. Is it now a bit more clear?
Yeah, thank you. This is now clear. Thank you.
Okay, awesome. Yeah. Yeah, please, I invite you maybe to check this. There's a paper also on talks extensively about this. It's Bratcher 2021. I believe this has been published in PLOS Combio. If I will write it here, maybe PLOS Computational Biology. So I invite you to read more about this. Also in the CDC Forecasting Hub, we have been using this calibration scores. Maybe later I will be presenting some references to those papers. You can also definitely read more there about this calibration evaluation. Okay, awesome. Thank you for the questions. Now I will start with the mechanistic models. So here we're going to do a quick review. This is a very just an area with a lot of research, very active. But we're going to go maybe to the basics and touch into some important concepts. The intuition of these models is that there are some people moving from compartments based on the disease progression. And there are the differential equations that describe how these people move across compartments. We can broadly classify these approaches into 3, maybe mass action models, ODE-based models, metapopulation, the second one, and the third one is agent-based network models. Regarding to the first one, now starting with approaches, maybe just for simplicity, let's analyze the SIR model, which is one of the most simple models. Here we have three compartments that you can see, S, I, R. S is susceptible, is people that are healthy that may get infected if there is a contact with an infected person. The infected people that is going to spread the disease through contact. And there are some also people that have already gone through the infected stage and have recovered from the disease. And there are some parameters also. You can see that there are beta and this delta. They are describing how many people or the ratio of people moving from one box to the other. But this is not just maybe a very direct thing, it's actually a differential equation, which I'm going to see in a moment. And there are some assumptions for this model. So this is a perfect mixing assumption. That means that any infected person can infect any susceptible person. So they are all together in the same kind of environment. It doesn't matter if you're family with it or your friends or it's unknown. You are assuming that they are all perfectly mixed. Also, for the specific SIR model, we have no births or deaths. Population is constant. And also we have this deterministic model. So these are the equations that for the SIR model. We have usually the number, so maybe let's explain a bit of these equations. This is the ratio that the number of cases are going to increase, so the infected people are going to increase. And this is basically the number of new infections, which is the beta parameter, the transmission parameter, transmission ratio, multiplied with infection attempts. Infection attempts is how many, so this is a multiplication of SII, because it's going to be that every single people in I is going to try to infect or have to have an attempt to infect every single person in S. So that's why we are multiplying SII and I. And then we are subtracting from this new number of infections, we're subtracting the people that are actually recovering, that now are being cured, right? There's delta multiplied by I. And when we are solving this SIR, we find that there is no closed solution, but there is a numerical solution. And we are going to maybe just go through a quick example of how do we do this with R. So let me go quickly to here to the. So you also have access to this RStudio cloud projects. So here, for example, we can enter. I believe you have access, and you can enter also to the R notebook. And we are going to start with the SIR. The other one we're going to do it later. And here I want to. There are several steps here that you can, if you can see, you can modify things. You can write, for example, your own values for beta. Maybe let me explain first the equations. The equation that we just saw. This can be written in R like this. Beta is I. This is a function, right, which takes the initial parameters, the initial value, what are the parameters that we are going to be using across time. And then these are the parameters that we may set up, and then we just let the simulation to run, and we are going to get some of these epidemic curves that we have seen before. Okay. So if you click, for example, in Knit, so we are going to be able to see the whole notebook being compiled quickly. You can play, of course, with this later. I just want to show you maybe some very punctual concepts here. That this is the epidemic curve, for example, where we look if beta is 0.1, but if we, for example, change beta, which is the transmission rate, to a higher value, we can play with this, and we can see that how the infected, the I, now goes more rapidly to peak more rapidly, and also it peaks higher. It peaks higher, almost 50% of the population gets infected, and then it goes down. So you can definitely play with this. There are other more resources available online that you can explore in order to understand more even this model and even more complex models that we are going to be looking at in just in a few minutes. But I just wanted to have this resource so that you can maybe start with some exploration. Now, there are many extensions to these SIR models. There may be some extensions that incorporate births or death rates. There are some variable contact rates, age structure models, and you can make lots of things stochastic, have even multiple diseases and viruses. I invite you to see these references if you are interested in learning more about these extensions. And also we may have this specific implicit solution for the SR model from which we can derive some interesting indicators. So if you have this differential equation, if you solve it and you will have this solution, which S, as you may remember, is susceptible. So susceptible over time depends on the initial value of the susceptible. And it is an exponent which depends on the R naught. R naught is a value that we are defining here. That is the n multiplied by beta divided by delta. And this R naught, let me tell you that is going to be useful across multiple diseases. It's called reproduction number, but it's going to be different for each modeling. If you have an SIR, it's going to be different for an SEIR. The calculation is different, but what it represents is going to be in the same spirit. And so basically what we are saying is that it depends on this constant that is depends on the transmissibility and also the ratio of at which the people recovers. And this then if we move to digging more into the R naught.
Just a question. The N there stands for the population?
Oh, yes, please. Yes, you're right. Thank you. I forgot to mention it. Mm-hmm. Yes, the N stands for population. And if we go to the, actually sometimes N is, it depends on how we are working with S, I, and R. Sometimes if we work with S and R as like proportions of the population, like for example, if S might be 0.99%, so you disregard the N. And I think in the next slide, we are going to disregard the N. So just a heads up for that. So now let's analyze this ratio in which the cases or the infections are increasing. So this ratio is going to be positive or negative depending on these values in which we can factorize. And because I is always positive, then it is dependent of this value, which is beta S minus delta. So if we want to actually make the epidemic to die out, to stop, what we want is that this value, the growth has to be negative, has to be decreasing over time. So that means that we want S to be less than delta divided by beta. And we put S0 because it's kind of the start. At the start, we want to start the simulation with this value below delta by beta. And this is so basically this is 1 divided by our reproduction number. So the interpretation of this, usually a basic reproduction number, is that is an average of secondary cases caused by one individual. And this is, as I mentioned, this is a threshold because if we're saying that this is 1 divided by R naught, what this means is that it's going to die out if this is negative. But if this is happening, the epidemic is going to die out because the ratio of growth of I is going to be negative. So we will have, this implies that we will have only an epidemic, a large epidemic, if our R naught is greater than 1. Hence, estimating this R naught is very important for multiple diseases, and especially for immunization, because if we reduce the susceptible population below 1 divided by R naught, so it means that if we vaccinate as many people so that we can make the susceptible people to be much less, then we can control the epidemic. We can control that it's going to die out very quickly, right? So these are examples of plots. If you have several values of R naught, you can see that this one is the smallest R naught, 1.05, and we can have up to 3 that it goes up very quickly and most of the population gets infected. There are, as I mentioned before, for each disease, we may have a different R naught. The calculation is, it takes time usually to calculate. There are some methodologies to calculate this. For example, for SARS, not SARS-CoV-2, but SARS, it was estimated in hospitals. And there was, because hospitals usually is a setting where perfect mixing is a reasonable assumption. It is a nice environment where we can calculate, but when we translate it to other environments, it's not going to be the same, right? It's going to be not homogeneous, it's going to be different. So that's why there's a variability even in R naught, variability also even maybe in locations. And finally, maybe just to say that this is still under investigation for many COVID-19 variants. So this is not a trivial thing to do, but it's important. Right? The second set of models in mechanistic models are metapopulations models. We can think of these as extensions to the previous ODE-based models. Here, what we incorporated in the special structure in order to incorporate to model the heterogeneity among contact patterns. So what we are going to do here is to have maybe one of these ODE-based models for a smaller population, for one community, and we are going to also measure how many people are going out and going inside the community. And for each community, we will have one specific ODE. So, for example, that's why we have here this sub-index I. For each community, we will have one effective number of X. X in this case represents X, Y, and Z, represents SIR for a state and city I in time T. This sigma represents the daily passenger flow from city I to city J, and NI represents the population of city I, and we assume this to be fixed. So in order to calculate, so now in this new setting where people are going out and in, we have to get actually an estimate. This is a mathematical trick where we are doing here to estimate of what is the effective number of susceptible people, X, and it's going to be depending of the people that are going imported cases maybe, or exported cases, or the exported cases, the cases that we are exporting, sorry. And similarly, we can do for the other Y and Z. Given that estimation of the X effective, we can put it with our SIR equations, beta I, as we saw before, and then we can estimate what is going to be the value for the next time step. And we can do the same for the other states as well, right? For Y, and Z. But as we know from our experience, human contact patterns are not random. We have different interactions. Even within our community, we have different interactions when we are maybe at the bus stop, or we are taking a coffee with a friend, or when we are studying. There are different interaction patterns. It's not that we are always close to each other, or we are spending the same amount of time with each social group. That's why, but why, how to capture them? How to capture these very granular patterns? And there are several recent studies on this. This is one example using cold data records. You can see that we have several locations It is even measuring how many time you're spending at the coffee shop, how many time you're spending at work, and then how many trips you're doing from one side to the other. So this is a very granular data that you can use in order to understand how the population usually, or what are the usual social contact patterns in the population. And there are several COVID-19 examples. There are data from Apple, coming from maps and directions, Google, Facebook, Instagram, and so on. Of course, there are some privacy concerns that we have to be aware of, and we should take in consideration that when we are doing this. But yeah, if definitely it is an interesting data set to explore. And this motivates the third group of our mechanistic models, which is the agent-based network models, in which each individual is an agent in a simulation. So we have the disease spread is going to be over contact networks, over these social contact networks. And in this way, we are going to be modeling the heterogeneous interactions between the agents. And some of the concepts that are relevant to these methods are social contact networks. And for example, twin cities, where you are basically replicating all the aspects of a city into a digital world. We're going to talk more about this, which is a more active research area, the social contact networks. So there are some first principles to constructing these social contact networks. You have to first understand individuals, who are what are the sequences of activities that they often do, what are the times of these activities, what are the places they go, what are the reasons for them. So for many of these, we don't have explicitly available data sets. And so we have to synthesize multiple data sets and put a lot of domain knowledge in order to create this. And also we can, of course, incorporate some behavioral changes over time as adaptable models to new behaviors. And this is a depiction of how we may create this. We use information available on one location, for example, all the information demographics, as I mentioned before, in order to create a synthetic population. And we are going to use as much real data in the step in order to get the activities, the locations, the routes, and that is going to be able to help us to create the social network, which is going to be a synthetic social network that we can use for doing simulations of the epidemic spread, right? So, and then we can even place scenarios that we want to evaluate. It is very useful, of course. It is very useful. As you can see, there's a lot of work also, but it's a very useful tool. And there are some examples in COVID-19 also. For example, this is an example in Massachusetts, where we have they have several layers. One is school layer, the other one is workplace and community layer, and the other one is household layer. And you can see that within each group, they are all connected and also interconnected with the other layers, right? So we have even one person can be here and here, right? So you want to have a different contact patterns, different people that they are in contact with at each layer. So now moving to how to calibrate these models. We usually have this equation. This is a minimization equation where we are minimizing the data R observed, or it can be I also, it can be what is available. And with the ones that we are getting from our model. This typical data includes these time series of new cases from surveillance, but there is a lot of problems with these data sets, right? There are missing data, biases, lags. For example, for COVID-19, calibration in infected cases is unlikely to be robust because there are several asymptomatic cases. But for example, mortality and hospitalizations are likely to be better because they are you have much less of these hidden instances for mortality and hospitalizations. Typically, what you put is some range of parameters in order to make the optimization work. This is a kind of challenging optimization sometimes, many cases to calibrate these models. So you require some expertise. And if you want to get uncertainty from the data, you may have to do some multiple stochastic calculations in order to get the uncertainty bounds that we were talking at the beginning, right? And then, so to summarize, maybe some pros and cons of mechanistic models. It has been the workhorse of epidemiology for 100 years since Bernoulli came out with one of the first models on this. They are easy to extend and build. For example, COVID-19 work we have presented already. There are some good numerical solvers exist for this. We can see, for example, dynamical theory, nonlinear dynamic chaos. If you're interested, you can also look how this relates to that. They are useful to get some intuition on broad principles, but often they are more qualitative rather than quantitative. As we saw, especially in the agent-based simulations, it's very hard to construct and even to calibrate, but they are very helpful to ask meaningful questions about what is going to happen, or understanding maybe the mechanisms of this spread within the model. But sometimes these models also, they miss many interactions, they don't reflect the reality. And also the calibration, as I mentioned before, is very challenging, and even a small deviation in the parameters may lead to very different results. Just some few remarks. There is a lot more to say about mechanistic models. This is a very superficial summary. I invite you to go to other resources for a more in-depth discussion. Our focus, as mentioned, is going to be in statistical models. We're going to be talking more about them and going a bit more in depth with them. And that is going to be the next part, which is going to be after our break, 15-minute break. So if we are going to be around here, we can feel free to ask us any question, unmute yourself or write in the chat. And otherwise, we will see you in 15 minutes. Yes.
Okay, thank you. Please, can you tell me more about a model, agent-based model?
Okay,
agent-based model.
Yeah. So, do you want to know what are the underlying ideas, the basic ideas, or do you want to know any specific about it?
Please go back for one slide, please.
Okay.
Yes, here.
Sure.
Look, the next one, please.
Oh, okay. One more. Okay.
Yes, yes. Okay, each India is agent in simulation. Okay.
So you can think of this individual. For example, there are red individuals here in this picture, red and blue individuals.
Yes.
So on every time step, the red individual may infect only the people that are in the contact network, right? So we are going to simulate based on also the probability of infection, and also and based on also the graph or this network that this person has. What is maybe the likelihood or the probability that this green person may get infected because it is in contact with 1, 2, and 3 infected people, right? So in each step, we are going to make that simulation. They make a simulation step that is going to be considering this, and this person may or may not get infected. It's a simulation. So and next step is going to happen the same. Maybe this person is going to be recovered, maybe going to be blue, and the probability that this person is going to get infected is going to be less. But this is going to be like a stochastic process, right? Every time it's going to be different.
Okay. Okay. Thank you.
Yeah, sure.
Thank you, Alexander. So we take a 15 minutes break and we come back on London time, maybe 3:15. Is that okay?
Yeah, sounds great.
Okay.
Hi, Alexander. Can you hear me?
It's me. I can hear you.
Sure. Yeah, sure.
Now,
we can continue. Yeah.
yeah, perfect. And now Harsh is going to continue with this part.
Yeah, sure.
Okay. Can you hear me?
Yeah, I can hear you.
Let me know when I can start.
Yeah, thank you, Harsh. We can continue now.
Okay. Hi everyone. I hope you had a good break. Now we are going to talk about statistical models, which have become more like recently have become more important and like have more significant impact in short-term forecasting. So these models are also called phenomenological models, and the intuition is that we are given a family of functions, and we basically have to find the best function that fits the epidemic curve or whatever task we are trying to accomplish. So basically, we will have a loss function as shown here, and H is basically the family of functions where we have to search over, and we find the function which best matches the ground truth Y over all the ground truth in the training data, which is from the past. One simple way of thinking about it is that we are forecasting for, say, a given season, for a flu season, and we are currently in some week 20, and we have data from week 0 till week 20, and we find the best function that fits the curve for this epidemic curve, and then we use that function to forecast in the future. And we use multiple approaches. The type of family of functions determine the approach we use. For example, regression models. We use language models which utilize languages like language data like tweets or search. And then we'll talk about deep learning neural models, which have become very popular, and also density estimation models, which focus on probabilistic forecasts which have good calibration, which aim to give good calibration. Okay. Regression models usually assume that linear regression models in particular assume that there is a linear relationship between the input features for a function and the output. So like a simple way of writing this is that you have a vector x of features, and the function f of x basically takes in the vector and then does a dot product with a fixed w, which is its parameter, plus some bias, and then gives you the output. And these x values could be anything. Basically, that's one of the advantages of statistical models, which is that you don't have to assume any specific mathematical insight into the features. So they can be anything, and they can have high dimensions. And some of the examples of such models are autoregressive models, which we'll talk about. Then also some models use search queries as features, word occurrences in text, and there are many more interesting data sets which you can use with regression models. One of the simplest ways to model a regression model is to use past values of the epidemic curve to predict the future values. So again, given an epidemic curve, so maybe you have an epidemic curve and you have to predict the future after this point. So maybe you can use the last k weeks values in the epidemic curve as features and predict the next value. So mathematically, it will be written as something like this. So here we have used the last p values of the epidemic curve to predict the values for the current week p. And we can make these models more complicated. For example, ARIMA, along with the previous values of the epidemic curve, also takes into account the differences between individual values. You can get more creative in like transforming the features and formulate such models. But in essence, they use only the values from the previous values of the epidemic curve. Now you can also use external data sources. One very interesting example is called Google Flu Trends, where they basically use the number of queries. Like for example, when you search for a word in Google, it records like number of people who have searched for specific topics, and then we can use these certain topics which are related to flu as the features in order to predict whether a population expects a flu outbreak or any future flu trends. For example, if more people are talking about running noses, maybe there is a flu outbreak, things like that. And Google Flu Trends was started by Google, as the name says, and they use some proprietary set of topics which no one is like the public is not aware of, and they use these to model the future trends. So basically, Q here is you can think of Q as aggregated variable that shows the number of queries which people have, number of searches for like specific topics related to flu which people have done for a given week, and you use this Q and a simple linear model with two parameters beta naught and beta 1 to predict the future incidence of flu. So this simple model actually received wide media coverage and had a huge impact in and showed that we can use digital indicators such as search queries, which is readily available in order to accurately predict flu, the future flu trends. And however, while it did provide this impact and insight about digital epidemiology, all was not good. Like over the course of time, GFT didn't perform very well. In fact, it failed to capture the famous H1N1 pandemic around 2009-2010, and also 2012 to 2013 season, it overestimated the flu values, the future flu values, and this was due to multiple reasons. One of them was that, remember that they had this proprietary list of keywords that they based their features on. So they probably didn't account for the shift in keywords. For example, one example which people have hypothesized was one of the keywords was Oscars. And since Oscars happened around February and that coincides with the flu season in some areas in US, it was fitting well to their model. But maybe on some particular Oscar season, lot more people starting to talk about Oscars, and then that, while that didn't have any correlation, like causation to flu, due to the prior assumption about the correlation, the model just overestimated the values of flu. And so these are some of the challenges which GFT faced, and finally it was shut down because people didn't rely upon it after 2012, 2013. Then people tried to improve upon this model. One of the most important innovations was Argo, which is called auto-regression with Google search data. And basically, there are two important improvements they did. One was they used auto-regression along with using the search query volumes, which GFT did. And GFT used a single variable Q, which aggregated all search queries. But here they use separate variables for multiple search queries. So these were the two important changes that they did. And they also tracked changing. They also constantly track the correlation between search queries and the flu trends in order to make sure that things were like if there was an drift in the data, they can make changes to the weights given to each of the search queries. So this model again has was very successful and provided very accurate nowcasting and forecasting estimates. And they improved upon this in a version called Argo 2. Argo 2 is basically an extension of Argo, but whereas Argo just focused on national level ILI prediction, Argo 2 simultaneously did both national level and HHS regions. So HHS, for people who are not in US, like the US is made up of 50 states, but the public health agencies divide the entire country into like 10 HHS regions, where multiple states come under a single HHS region. So the goal is to predict not just national level flu incidence called ILI, but also at each HHS level. And they did it in 2 iterative steps. The first one was to use Argo model for independently predicting for each national level and HHS regions, and then also to include interdependencies between the regions. Like, for example, there may be some correlation between the flu trends in New York and maybe flu trends in Atlanta, because people usually migrate between these 2 hotspots for multiple reasons. So to capture this, they use a multivariate Gaussian model on the independent predictions to refine these predictions by using learning covariates across regions. So basically, they learned a covariance matrix between multiple regions R cross R, and then they if you have region level predictions U1 to UN, where there are n regions, they modeled refinement term PI for each of the regions as a multivariate Gaussian between from U and sigma, using U and sigma, and then this refinement term was again added to the prediction. So in essence, they captured the inter-region correlation using this covariance matrix. So next, I'll talk about another class of models called language models. In specific, I'll talk about a work which uses Twitter data in order to predict H1N1 pandemic. So this work uses something called topic models. So in essence, topic models basically given a text, a topic model is basically explains the generation process of the text by clustering each word into topics and then providing distribution over topics. So I'll explain to you in terms of these papers to make it in terms of the forecasting for pandemic, to make it more simple. So you have this multiple a data set of tweets which are related to flu, but these tweets could provide information in terms of what is the current state of the individual who is tweeting. Maybe they are susceptible, which means that they do not actually have any symptoms yet. So it's like had a good night's sleep this morning. So very generic tweet. Then maybe the next state is where people are in have gotten infected, like they're describing some symptoms, my neck hurts or something like that. Then they are hospitalized and the next state, and then finally they're in the recovered stage. So these words in these tweets will basically give you an idea of the current state the individual is in the entire infection cycle. So the topic model basically it maps a tweet into these hidden states, SEIR. We don't know these hidden states, and it's very hard to find out these hidden states. But we can make the model map these tweets into these hidden states, and then figure out the transition of the individuals inside these hidden states. So, for example, the model is basically like if you are in state S1 on day 1 and you are in state S2 on day 2 and so on, and at each of these states you provide some tweets, and then these tweets are observable, but these states are not observable because you're not constantly monitoring them. But you can use these observable data in order to understand the transition dynamics of the states over for the population. So that's what they've done. And then for like you, this model basically learns automatically like which tweet comes in which state. For example, in a state, it's generic words like music, work, and in E state, it's more about symptoms. In I state, it's more about the actual disease, what they're suffering, and so on. And so to get a little bit more technical, they use a variation of hidden Markov models, which if people have heard of it, in order to get the generative process of these tweets. So for each tweet will be in a topic, and also these topics will be like for each tweet there'll be a topic, and each of the topics will go to a state, and these states are change over using the transition dynamics similar to the transition dynamics of an SMM model. And then you learn the parameters of this transition dynamics and the like the assignment of the topics to tweets and so on using an EM algorithm similar to hidden Markov models. So the overall takeaway is that these topic models provide a way of interpreting the dynamics of how people tweet and like combine them with the infection cycle. And this is another way of utilizing digital data like text data to capture the epidemic dynamics of population. Okay, so now we will go over another demo, which basically shows us how to use these simple regression models, and we'll basically use two models. One is ARIMA, and another is a neural network, which Alex will talk about after this. Yeah, so this is there in the COVID forecasting R&D. So okay, right. So in the notebook folder, you will have a dataset called COVID data US national.csv, which contains for each of the weeks, it contains the number of deaths and also other features such as mobility, number of tests, and number of cases detected. And if you plot the death number of mortalities over the weeks, you get curve like this. Like notice that in the first few weeks of 2020, there was almost very little cases. Then there was a spike, and then we settled down a little bit.
Sorry, we cannot see your plots.
Oh, okay. Okay, is this visible?
Yes. Now let's go.
Okay. Yeah. So yeah, I'm just going over the notebook. As I said, you have a CSV file which has the some of the features along with the number of deaths due to COVID for the past year, like 2020. And if you plot the death trends in 2020, you see that initially there was very little death, and then there was a spike, and then things started settling down. And also there are other features like COVID cases, mobility, number of tests, and so on. For example, COVID cases, again, there was increase over time. as the pandemic started spreading. And our goal is, like the goal here was to basically predict the future death trends given the data from the past. And we use two models. We use two models, ARIMA and a neural network. Neural networks we'll talk about it later, but we will just showcase how to do it in R. So one of the first things which people do when they're doing data analysis is to first do some small pre-processing. And since the features are of variable ranges, we do a min-max normalization. So make the values between 0 and 1, and then start modeling. So both the ARIMA is off-the-shelf ARIMA, which is used in like R gives you a package for ARIMA, which works well. And then we also use a neural network called using the neural network library. And for this neural network, we have used, like, a neural network basically has multiple hidden states. Okay, maybe I can. Okay, so a neural network is basically, in very simple terms, you have a set of features you give as input, and then there are multiple hidden layers, and then you have an output. And in each of the hidden layers, there is some linear combination of the features from the past hidden layers, and there is some non-linear function after you make that combination. And here in our example, we used a 2 hidden layer network, simple 2 hidden layer network with 10 and 40 hidden layers. And you can change these hidden layers and see if you can get different results. So for ARIMA, also you can like, there is parameters called order, there which are 3 integers, and usually higher the number, the more complex will be the model for ARIMA. But here we have used 2, but higher complexity also sometimes means that there will be it won't converge well sometimes. But here we have used 222, which gives a reasonable result, and you can try to tune these values and see if that helps. And finally, we observe that ARIMA, ARIMA actually does slightly better than neural networks, which is surprising since, like, people almost everywhere use neural networks for everything, and that's like usually the go-to model. And we will talk about some of the reasons why using a simple off-the-shelf neural network doesn't work in general. Yeah. So yeah, go over this notebook sometimes later. And yeah, I think that is with respect to the demo. I think Alex will take over from here.
Yes, thank you, Harsha. So I'm going to now start with the neural models. Yeah, okay. Yeah, now it's working well. So yeah, as Harsha introduced, thank you, Harsha. He introduced also this architecture of deep neural models. So maybe let us take a step back and then say, why do we even think about deep learning in this domain? This is useful because it can capture nonlinear patterns in high-dimensional data with very minor assumptions about the data. As Harsha also mentioned, it's very flexible in learning rich representations. They can leverage data sources of a variety of modalities, even images. You could include even images or language models. That is not non-trivial to do when you have other modeling techniques. So here we have a lot of very rich toolkit that can help us to leverage the different modalities of data. And for example, a more specific example for flu, for example, there are some composite signals that are really challenging for calibration for the models, because in the case of flu, it's a mix of multiple strains. There are multiple viral strains, even other diseases that are being accumulated in the metric that we are using for flu. So using mechanistic models as per se, it is very challenging to do this. So this is also motivates why we can maybe leverage these neural models that are capable of doing this in other domains also. So some of the considerations that we have to think about when we are doing we are using neural models. One of them is the disease spread. We want to incorporate information about disease spread. We want to model spatial transmission, incorporate mobility information, and the data that we mentioned before, mass adoption, social distancing. Many of these things we can incorporate in data, but the data by itself in nature is sparse. Sparse means that it is scarce and is sometimes not representative of what is going to happen in the future. There may be some shift in the behavior, and that is going to be very challenging to capture only from data. So what we can do is to use some methods in order to maybe extend this data set that we may use in order to overcome the sparsity of the data. But this is important to have in consideration because, you know, for example, what Harsha presented is just a simple neural network. They usually require a large amount of data in order to make it work properly. So therefore, we have to go deeper into what are actually some methods that we have to craft, neural methods specifically for this kind of domain, so that we can have good performance in forecasting. And also there are some challenges that we are also going to talk a bit later about, maybe data revisions. Data revisions are, for example, that the data that is initially released, that is going to be changed later on because there are maybe they didn't count correctly the cases or the dates. So they are going to, in the subsequent weeks, they are going to correct it. So we are going to also discuss about that a bit later. And of course, anomalies also, we want to be robust to anomalies. So these are challenges when we are dealing with neural models in a sparse domain. And utilization, sometimes neural models are being thought about a black box, that we cannot get much insights from them. But there are some techniques nowadays that we can use in order to get some interpretability of what is happening on it. And of course, uncertainty codification is a recent research area in also neural networks, in which we can leverage in order to provide a more actionable forecast for decision makers. So having this, we have identified that there are several modeling ideas in the literature. I'm going to talk about 3 of them. The first one is modeling dynamics via similarity. One of the motivations for this is overcoming data sparsity and also enabling interpretability of these models. The second second modeling idea is transfer knowledge representations. We want to leverage what we are learning from other relevant domains. And the third one is incorporating a spatial structure. We want to model the spread about over adjacent regions. And basically, if we have a network of adjacent regions, we will be propagating across that network. And how do we model that with neural networks? It is also an interesting topic that we are going to be looking at briefly. So regarding to the model idea 1, modeling temporal dynamics via similarity. So for example, let's pay attention to these 2 epidemic curves. This is for influenza, and you can see that the green line is 2010 and the red line 2016. So these are very close to each other. And we can also find this similarity also for these 2 other curves, 2012 season and 2013 season. So one question that we can do is, can we leverage these similarities so that we can maybe perform better in forecasting? We can see this in the training data and the historical data. So given that we have only observed until here, can we use the information for similarity to make predictions here, or make these predictions? So the idea of this work is to cluster for prediction, cluster find clusters of the seasons and what are the most similar seasons to this, so that we can make these predictions. But actually the similarity evolves over time. At the beginning of the season, maybe that, for example, this season is more similar to 2012, but during the peak it is more similar to 2003. At the end of the season, it's more similar to 2009. So it's a dynamic clustering. We have to change across time. We have to change to which cluster or to which season it is going to be more similar. So what this paper is proposing is to do a deep clustering, where we are going to have dynamic clustering over the weeks. And this also helps to overcome the data because it has more support, it has more extra information, the model, so that it can perform also better in prediction. And just to maybe restate what we were saying, given this current season and given the historical seasons, we can see the similarity between this snippet of the current season with the snippets from the historical seasons. And we can leverage what happened after this time t, so that we can also help prediction in the current season. So this data-driven approach is called EPD. It is a paper from our group at Little Lab in 2019. This is one of the first approaches for deep learning approaches for influenza forecasting, and it performs very well. And it does in multiple targets, as I mentioned before. Sorry, I didn't mention that. It is here a peak value, peak time, onset. There are several targets that are relevant for influenza that this model was predicting. And experiments, we are going to see some of these baselines in a moment. We already saw the ARIMA one with Harsha. I remember ARIMA was actually beating the neural network. We will see that this is not the case. Here, with these additions, this neural network is being able to perform better than ARIMA. For empirical base, this is an approach that we are going to see in the next section. And this is a historical average of previous seasons. Again, then is something similar to the idea that it has, the method has about the clustering. So as you may know, it's a clustering approach. And LSTM is just a simple off-the-shelf neural network that it is kind of very similar to our method. It's kind of a part of this method, but it is only one of the modules, right? The other important module for this method is this part, which is the clustering part. So comparing with these baselines in the national region, this model EPD, which is the red one, is outperforming the error, having less error in all of the tasks, in most of the settings, in most of the settings in national region, and also in other HHS regions, as Hutch introduced also this concept before. So there are other examples about modeling temporal similarity. We can find in literature that there are some temporal and geographical similarity across adjacent regions. There is also intercity similarity. Here, what they are searching is, given this epidemic curve, this is a cumulative confirmed cases epidemic curve, where they are searching across multiple other countries whether these maybe some segments of this epidemic curve are similar to other segments of the epidemic curve of other countries, and they are using that information to make better the predictions. So that is also another way to incorporate this idea of temporal similarity. A small detour about this, there is another interesting problem here that we can think about, that is incorporating guidance in epidemic forecasting. Here we have some epidemiological expert that may notice some ideal behavior in these neural models, and with some constraints when during training, we can incorporate or make the neural models to have a better behavior that's more desirable. For example, that they have smooth predictions. Here in this case, often the neural models, when they see this Christmas tip, Christmas tip is basically the reporting issue that during Christmas the reporting decays. People is the hospitals that they usually report information, they are not working as usual, which is understandable. But when we are seeing this, a small dip in the epidemic curve. And if a neural model by itself, what it can do is that it thinks that it's actually going to start going down, or it may overcorrect. It may even do this very high correction. And in order to avoid this, we can impose some constraints during training, like smoothness. Another case can be that the neural models may have some good surveillance data in urban areas, but other bad surveillance in rural areas. And we may have some problems of equity among regions. So also we can incorporate some equity constraints and make this forecast more desirable or have a better behavior. So this is another exploration area that we have been doing. Now going back to the modeling ideas, there's modeling idea 2 is a transfer knowledge representation. And here, what we want to understand is they make the neural model is automatically learn what to transfer, and not all information is relevant from, not all information, we need some selection, some filtering. And some examples of this transfer of knowledge, for example, we can have that we want to transfer some information from one country to another country. Even if they are very far away, they are in different continents, there may be some relevant information that we can take. In other case, we may have that we have a historical scenario and a novel scenario, and we want to transfer some information, some knowledge that we learned in this historical scenario to this novel scenario so that we can perform better. And this is an example of this was with pre-COVID flu. After the COVID pandemic, when it started, we had some COVID contaminated flu counts. And let me linger a bit on this. So early in the pandemic, in the COVID pandemic in March 2020, because flu counts are syndromic, means that they are symptomatic people, and COVID and flu, they have some similar symptoms. So there were some COVID cases that were being captured by these flu surveillance systems. And there were some anomalous behavior. Now, for example, these peak and peak, these are due to this COVID contamination. And we even can see it more clearly here. We have that the gray lines are other historical seasons, and the black, more darker line is the current season, the season 2019, which was behaving in a different, is very different than the previous seasons. We had here a peak, a third peak, it was unusual. And as I mentioned before, this peak may have been because of the COVID contamination. And actually after that, because the recommendation of public health authorities was not going anymore to in person to hospitals, there was a shift in healthcare seeking behavior. So in this new scenario, still we have people going to hospitals. CDC wanted to have information on how this epidemic curve is going to evolve, and models that were trained with only historical data were failing to capture these new trends or adapt to the new scenario. And you can see here the historical models are having a hard time in this new forecasting setting. So what we need to do is to adapt these models. And what we have seen, it is a work from our group. We saw that there were some COVID-related signals that correlate very well with these new trends. And we can use these signals to in some part of the epidemic. For example, the COVID-related signals are going to be here in the green box, and they are going to be most useful in the green part. But the historical influenza models, there are some patterns that we can use in order to predict how it's going to be the decay. So we have to use information from both of these at the same time, and we have to make the neural model to select from which part is going to use first, and in the blue one it has to use mostly the historical data. So therefore, in this case, that is why we propose is what we call attentive transfer learning, which enables this transfer of knowledge from a historical model. In this case, it was the EPD model that I also introduced, to another model where we have even more signals, more data sets that are newer and are more correlated with some part of the epidemic. So another modeling idea, the modeling idea three that we were discussing, is a spatial structure, incorporating a spatial structure. So as you may have also some intuition that pathogens propagate through contact, usually to adjacent regions, population, and then after that, once we propagate to one adjacent regions, these adjacent regions also propagate to even more further. So these are basically a propagation over the spatial graphs over time. In order to model, some people have proposed, for example, this method, which is based on graph neural networks. Uses the graph neural network to model this propagation, like which is technically, I'm going to use a little bit technical, is called graph message passing. Is passing some message or some information from one node to the other, and then to the other, and then to the other. So we are emulating this propagation process with this module. And there is another module that is dilated convolution, in order to incorporate some information about the sequence of the sequence, like a sequential information of, for example, this epidemic curve incorporated with dilated convolution, and the graph structure is going to be coming here in the graph neural network. And all of this is going to be added here. For example, here we have just a vector. You can see a vector for each instance we have. We have a vector, and then these vectors enter to another neural network that makes the predictions. So these are some recent neural models that have been proposed. And now Harsha is going to also discuss about other family of models, which is density estimation models. Harsha, do you want to share the screen, or should I keep it later? You're on mute, Harsha.
I'll share the screen.
Okay.
Okay. Yeah. All right. Okay. So in the density estimation models, so far we have talked about models where the output is the future forecast value, but usually we are interested in not just the single value for the future forecast, but also the entire distribution of the forecast, in order to capture the confidence interval, the uncertainty the model has with respect to the forecast. So density estimation models basically do that. They directly capture the forecast distribution, or at least attempt to do that. And so in essence, the output is the entire forecast distribution. So they can be divided into two types. One is parametric and non-parametric. So in parametric density estimation models, the output is basically the parameters of the distribution Like, for example, parametric distribution is a normal distribution where the parameters are the mean and the covariance matrix. And so the whole process is basically to estimate these parameters. In non-parametric models, they leverage directly they leverage the similarity between the training data point and the training sequences and the input sequence in order to like provide a function that the function is basically the function of the training data point, and that function is the probability forecast distribution. We will look at these examples to make it more clear. One of the example of a parametric model is called the empirical based model, where the idea is pretty simple. They assume that the current season's epidemic curve has similarities in features with respect to the previous season's epidemic curves. Some of those similarities include the shape of the past sequences, and maybe another parameter is peak height and peak week, like when the epidemic curve's highest value is and what is the highest value, and also some scaling factors. So maybe a past epidemic curve looks like this, so you might want to scale it a little bit down or like squeeze it a bit. So these are the parameters which we predict for a given current season. So these parameters are not a single parameter, but there is a distribution. For example, you could have a uniform distribution over the entire past sequences. You can have some kind of normal distribution for a peak week, normal distribution for a peak height, a peak week you can use Bernoulli distribution, and scaling factor again you can use the normal distribution. So you use this distribution and you set them as priors, and then based upon the data which you get for the actual current season, you like update the parameters of these distributions, the uniforms and the normal distribution, to make your current season fit more closely as you get more and more data across weeks. So this is basically the process of Bayesian inference, where you have a prior distribution and then you keep updating the parameters of the distribution based on what you observe. And this model, along with another model, I'll talk about another model which does something similar. The idea is something similar. That's called delta density. But here, instead of using Bayesian inference, they use kernel density estimation. Basically, kernel density estimation means that the function, the output distribution function, is contains kernels between the current season set t and the past season t dash. So these kernels ki's measure some kind of similarity between current season's curves and previous season's curves, and they're usually more efficient to measure the similarities rather than compute the exact characteristics of the curves which we are measuring. And so I won't go into the details, but if you're interested, look up kernel regression or kernel densities using kernels like for SPMs and stuff, and you will find out why kernels are a very important topic in measuring complex similarity measures in data. So they use this kernel density estimation. Again, the idea is same. You use similarity with respect to previous data sets, and to get the parameters of the distribution. And then they have these two models, empirical based and delta density, have been some of the top performing models in the flu site challenge, which is organized by CDC in order to predict future influenza incidents. Yeah. So another recent work was to use Gaussian process-based models, which are another a very popular density estimation models. And these this simple Gaussian process-based model also provided very reasonable confidence intervals and also very accurate forecasts. And yeah, so these are the density estimation models that have been classical density estimation models that have been successfully deployed for epidemic forecasting. However, they're not all they're not perfect, and in specifically they don't focus on calibration, especially when there is when we encounter some kind of novel patterns, Like for example, during the 2019-20 season, there was a third peak in the epidemic curve, which was not usual at all. And this was probably due to the COVID cases that happened, like as Alex talked about. And most of these models, since they relied upon past data, since they overly relied on past data, they couldn't adapt to this, or even if they adapt to this, some of these models provided very super confident confidence intervals, and they were horribly wrong. So these have, so basically they were not well calibrated and they were not very accurate. And our goal was to improve upon this using neural methods, neural network methods. And why neural network methods? Because neural networks, as Alex has emphasized, are well suited for capturing complex sequential patterns, and hence we can utilize this to also adapt to this novel situation. But the previous methods usually are using point forecasts, and we have to adapt our neural method to provide probabilistic forecast. So we combine the neural network model with the Gaussian process-based approach, where we use the neural network model to provide some kind of representation for each of the for a sequence, the current epidemic curve, and then we leverage the similarity in these representations, which are derived by the neural network, using the Gaussian process-based approach to provide forecast distribution. And the entire pipeline of our model is a little bit involved, but the main idea is that we first use the neural networks to encode these sequences to vectors, and then we leverage the similarities in this vector space similar to Gaussian processes in order to provide the output distribution. So it's a marriage of the best parts of both neural networks and the flexibility of non-parametric models. And indeed, we got good success using this method. Specifically, we saw that our forecasts were well calibrated. So I think Alex has talked about what is a good calibration. That is, if the confidence interval match the fraction of ground truth that lies in the confidence interval over time. So our model was close to, like, almost exactly matches the fraction, whereas other models slightly deviate from it, and some of them deviate very largely. And we also adapt to these novel patterns, as we've seen before. Like here, the red curve is our model, and the red highlight is our model's confidence interval. So the confidence interval covers the ground truth. And also, because we use Gaussian process-based model that captures similarity, we can also do some reverse engineering and figure out what are the similar patterns from the previous season that led to our prediction. And this helps in providing explainable forecasts. Like for example, for the current epidemic curve, which is in the dark blue, we have found that some of the curves which are similar to it as found by the model were from previous seasons. And these curves indeed show similar patterns. So we can reason about why, like, what are the similar patterns which are captured by our model, and explain the model prediction more reliably. And finally, yeah, so this is basically the entire landscape of statistical models. And so far, statistical models have outperformed mechanistic models in short-term forecasting. They're also doing well in calibration and uncertainty quantification. And however, and there are data-driven models which can be flexibly, where we can use multiple features flexibly without worrying about actual, like, unlike mechanistic models where we have to provide mathematical reason and build a dynamics based on these other features. However, there are some challenges for statistical models. Specifically, we do not, as we try to forecast for longer term, the performance of these models quickly degrade. And also, we are unable to, like, provide scenario modeling. For example, if we, it's not interpretable, right? So you just give the input and it gives you the future forecast. So asking questions like, what if we increase lockdown or decrease lockdown? What if the infection rate of this disease was lower? Then what happens? Such questions cannot be easily answered by these models because they're essentially a black box function which just takes in the input and gives you the future forecast. So these are some of the challenges of the statistical models. I think we'll have a break now and then we will continue in the hybrid model. Am I right?
Yes, correct.
Okay.
So we can reconvene maybe 15 minutes. Me, it's okay.
Sorry, can I ask you a question?
Yeah.
You mentioned that these kind of statistical methods works like black box. I didn't get it right.
Okay. So basically, for example, if you have a neural network, it's basically a very complex model with like thousands of weights, and then it gives you an output. So you give it an input and it gives you an output. So for example, you can ask a question like, if you want to think about like, what if there is a variant of a disease? Say maybe there's a variant of COVID-19 which has infection rate ×2. So you can't capture this directly using this model. Whereas in a mechanistic model, all you have to do is like maybe tune beta a little bit. Then you can like run the beta, which is infection rate, a little bit, and then run the model, and then it gives you a projection of what would have happened. But here, since the parameters of the models are so complex, and you don't know exactly what these parameters mean. So in mechanistic model, you know what exactly beta means, but in a neural network, you don't know what these weights of these nodes mean. In RMI, you don't exactly know what the weights of the linear weights mean. So you don't know the meaning of those weights. So you can't do this kind of counterfactual reasoning very easily. So that's what I mean by you can't use it as a black box. So I mean, the statistical models are basically a black box, and you can't do interpretation very easily.
Okay, thank you.
Okay, thank you, Harash. And we can take a 15 minutes break now, and our meeting will be start at 14:30 London time. Thank you, everyone. Alexander, can you hear me?
Yes, we can hear you.
Yeah. Could you continue, please?
Okay, great.
Thank you.
So
Yeah,
I'm going
great.
to share my screen now. Now for the next, so for the rest of this workshop, we're going to talk about hybrid models first, then move to ensembles, and then enter to some practical considerations in epidemic forecasting. So first, let me talk about some hybrid models. Here what we are aiming is to use both mechanistic and statistical components as complementary pieces. So basically, here we want to take advantage of the expressivity of statistical models and also the theory-based mechanisms for mechanistic models and find ways of how they can complement each other, right? As I mentioned also before, statistical models are able to ingest multiple data sources, and that is also an advantage which mechanistic models may not have, and this combination may have these kind of advantages for mechanistic models, right? So in general, there's two big groups of these mechanistic models. I'm going to talk about discrepancy modeling and also this parameter estimation with statistical methods. A parameter estimation is for these mechanistic models. So in discrepancy modeling, we aim to make the statistical model resolve the discrepancies between another model, which is often a mechanistic, and ground truth data. In other words, the statistical model is going to refine or correct the other model. And here's an example for this. It's a hierarchical Bayesian model. In this hierarchical Bayesian model is going to refine mechanistic predictions with the hierarchical Bayesian model. Let's say that this is the ground truth data I-line. Each of the rows we have here is a year, a season. This is influenza data. So this is every row is an influenza season. And for each row, we can have a fit of what is going to be the SIR calibration fit. We are going to have a different fit, as you may see. Now we may have some refinement components that we are going to define, and we have to put some hierarchical base parameters on top to them. One of them is the common discrepancy, which is going to be for let's say that this is all of these epidemic curves are for one state. So it's going to be a state-specific deviation or discrepancy that we are going to add to all of these SIR epidemic curves. Then we're going to have also an individual discrepancy. For each of these seasons, we may have a different behavior that we are also going to be able to learn. And the sum of these three, the mechanistic model, the discrepancy that we are learning via a statistical model and based on a statistical model, and then another statistical model that is learning also the individual discrepancy. By summing this, we are going to be approximating closer to the actual behavior of the epidemic curve. So as you can see here, we are complementing both of these methods for complementing the mechanistic model with statistical predictions. Another group of methods is parameter estimation. Here, this is an example where we have a two-layer Gaussian processes. The upper layer is going to take country-specific features. This is the X. These are, for example, the demographics or economic situation of each of the countries. And in B, we will have what are the policies in place. These are dynamic, so these are going to change over across the pandemic. And based on these two features data, we are going to estimate what is going to be the R0, and this R0 is going to inform the calibration of a mechanistic model. Then the mechanistic model makes a prediction, and this prediction is refined by other Gaussian process layer. This is a lower layer Gaussian process that is refining the prediction. So Gaussian process here, it makes sense because we have a little data. We can, what it internally does is to cluster the, for example, the country features and policies in a latent space, and then can find similarity, and you can leverage that similarity in order to find what is the most appropriate R node. And what we are doing here is we are taking advantage of the experiences in other countries. Similar, for example, let's say that we had in the UK, we had like the Delta wave before coming to the US. So we can leverage that experience, put some, learn from similarities between these two countries, situation of these two countries, and estimate the impact, which is measured in the R naught to the, maybe to the US or another country that hasn't gone through that variant yet, right? So this method, they use, one of the nice things about this method is that it allows to answer counterfactual questions based on a new set of policies. So as I mentioned before, here we have P. We can maybe change because X is demographics, economics. This doesn't change, right? But in the future, but this one we can change it, and we can see, oh, what if we put a different policy? And these policies are usually encoded as a binary variables. So they are going to be, for example, whether or not you have school closures, 1 or 0. You have mass mandates, 1 or 0. And then you can put a new set of policies encoded as P, and you can have what is going to happen. For example, if we put a strict policy, a loose policy, or we just remain, we continue with the current policy, and then evaluate what would happen. So we are here combining these two in an interesting way, combining these two modeling approaches. So now moving to the ensemble approaches. Ensemble usually is a combination of models. And this combination of multiple models, it can be very different from each other. They often lead to a more robust forecast than any single model. And this has been found not only also in machine learning, statistics, and also in epidemic forecasting efforts for influenza, for dengue, for Ebola. Constantly, this finding is being drawn, right? That these combining models is often the most robust method that we have available. And it is understandable because making decisions, in order to make high-stake decisions, we need more than one model. And this is an example when the White House officials, Dr. Birx, she was relying only in the model HIME, and this model was saying that the epidemic was going to die out, and making this is a strong statement, and also relying only one model can be dangerous for decision making. So diversity is very important in this space. The COVID Forecast Hub has been using multiple COVID-19 models from US and even overseas. There have been groups from overseas or other countries have been participating in the US COVID Forecasting Hub. Here are some examples. For example, the HIME, they updated the model. Now it's a hybrid modeling approach. This is a meta-population model that we also talk about, classical comportamental model, data-driven deep learning model, and so on, right? So we have this diversity of models is a strength for an ensemble. And there's also one question is how to weight these models. Do we weight them equally? Do we take the mean across them? Do we take the median across them? So there has been some experiments that have been done within the forecasting hub led by Professor Nicholas Reich. And this is a slide that the group made. And they found that that usually often using the median is more robust. That is the official ensemble that is being used. And also recently they have been working on using variations of weighted median, and also, for example, selecting only the 5 or best 10 individual models in the recent 8 weeks. And from that subset, they are going to weight the models, or they are going to maybe put some equal weights to all of them, and they may lead, that this may lead to a better forecast. Why not the mean? Because the mean sometimes, if there is a model that unfortunately there also happens that there is a model that over predicts by a very high value, this is going to take the mean up very off, and this is going to lead to very bad behavior. So they have found that the median is often better and more robust. And the takeaway usually is robust, take a robust trained ensemble of a few models maybe, but I'm using a weighted median in this case. So these are the findings that for the COVID forecast hub in the US. Also, as you can see, the COVID forecast ensemble, which is the red, based on the median, is often the best model, consistently very good across the pandemic period, right? And we can see more of the results for these ensembles and also the models, the top models that I talked at the beginning in this paper, Kramer, which is available in medRxiv. So as a takeaway from these experiences, all models are being useful regarding a useful. No model is always good. And the top forecasting models, in fact, are usually a combination mechanistic, statistical, hybrid. So they are these modeling approaches are all useful, and they are providing different informations. For example, their usefulness may depend on the uptrend. There are some models that are very good at picking the uptrends, but later they overshoot. So we have seen that with one model that is very interesting. The researcher is very active, but unfortunately, they all after the uptrend they always overshoot, but very dramatically. So that this this makes us think that you have to combine always, and this is a very still challenging research question to understand when to use which modeling technique. So therefore the takeaway will be to just let's take all the models and then use them all together so that we can get a robust estimate and usually more informative about what's going to happen. Also, there are also another line of work is super ensembles, is very related. Here, it is not that there are many groups forecasting, but instead there is only one group that is fitting multiple models. For example, autoregressive AR, ARIMA, AR spatial with spatial structure, autoregressive with spatial structure, LSTM, mechanistic SCIR, and this one is also a mechanistic model but based on Kalman filters. And they are combining them even with some, remember they are even mentioned when they were presenting, even have some expert predictions also, that can be also something useful. And on a weekly basis, they are combining all of them, and they are making one single prediction, getting confidence intervals from all of these models, and they are submitting the forecast. So that can be also a valid approach that some people are exploring. So now we're going to move to the practice of epidemic forecasting. I think Harsha is going to take the lead in this section.
Okay. Shall I share the screen?
Yeah, as you prefer. Do you prefer to share screen? Yes.
Yeah.
Okay.
Okay. So currently, we've gone through a whole lot of the epidemic forecasting pipeline, which Alex has initially hinted on. And so we have done we have looked at data sets, we have looked at different kinds of models. And now we finally look at how it's the important details of how it's done on the ground. Like we talk about the initiatives, the infrastructure, the decision-making aspect of it and things like that. US specifically, I'll discuss about some of the initiatives which CDC in US has done first. Like we have they've set up forecasting initiatives for influenza, dengue, malaria, and West Nile, different diseases to track the outbreaks over time. And this has proven to be very useful in order to collaborate and improve the epidemic forecasting infrastructure. And also specifically for COVID-19, there have been, of course, there is the US COVID-19 forecast hub, which Alex has talked about with regard to some of the ensemble models. And there have been other countries also which have done something similar, like the German and Polish forecast hubs, which has been merged into the European forecast hub. And CDC has also recently started the scenario modeling hub, where we talk about where we focus on discussing different scenarios of like what if scenarios, and reason about the counterfactual scenarios and how we can prepare for it. And also there have been, for example, due to the result of COVID forecast hub, there has been some standardization of these forecasting benchmarks and how to report the results, and how to organize and combine these multiple predictions. For example, for the COVID forecast hub, each individual model's predictions are stored in specific formats and publicly available, and it's very accessible. So next, we talk about some of the challenges which we faced for real-time forecasting and some of the innovations which were done due to that. Specifically, we'll talk about recent work which has been done by Alex and collaborators in our lab called Deep COVID, and that focuses on some of the challenges of real-time forecasting. One of the important things is that there was a need to specifically modularize different aspects of the real-time forecasting, which includes the data module, prediction module, and explainability module. For the data module, there have been certain challenges with regard to data quality and like imputation, aggregation of features, normalization, all of these. And for the prediction module, like initially during the initial COVID-19, when it started, the data set was very less. Like we had very small number of features, the time periods. So we had to do some bootstrapping and also auto regression. Like we used the predictions of the model from previous weeks as part of the data set, and we had to do all of this engineering in order to improve the neural model, which is data intensive. And also finally, the explainability module. Since there are multiple features which we have combined into the deep COVID setup, there are sometimes like it requires us to like figure out which of the features are more important, and also like how these importances change across seasons, across time due to different circumstances. And I'll go over the main results of this work. The details of the neural model is available in the paper for those interested. So firstly, Deep COVID anticipated some important trend changes. For example, this early peak in this sudden rise in the death counts. Like most of the models, including ARIMA, would probably have not guessed this sudden rise in death count, which Deep COVID has done. It has also looked at some of the micro patterns in the forecast in the epidemic curve. Like for example, there is this almost periodic final grain patterns. Like for example, during the weekends there is lesser reporting, and during holiday seasons there is lesser reporting, and these micro patterns are also captured by Deep COVID. And finally, with regard to the overall performance, Deep COVID was actually performing better than the COVID Hub ensemble in point forecast, and performed comparably well even in the probabilistic forecast. And using the explainability module, we were able to like do some kind of analysis on which of the features were important for prediction and in across time. And like, for example, some of the reasons uh, uh, like like during the like during some of the weeks, the mobility was the main driver in for the predictions of the model, which all of these were important indicators of what the underlying dynamics of the epidemic, the complex epidemic which we faced. And finally, we submitted our predictions to the COVID forecaster. So we were placed top 5 among all the individual models, and our predictions, we provided predictions for more than one year, almost 1.5 years, for all the 50 states and the national level from 1 to 4 weeks ahead. And combining these predictions, we were placed in the top 5 over all the models participating in the hub. So some of the main takeaways which are important during real-time forecasting, which is a lot messier than just figuring out the model and just using the data available, is that there are multiple data sources which vary over time. For example, the reporting standards varied over time across each state during the pandemic, which we have to take into account. And we have to select specific signals which are important for prediction. There will be some delays and errors in reporting, and some temporal misalignments, and also spatial misalignments, because there is different reporting infrastructure across state and county level and national level. And finally, data quality, and also there is some missing data, or usually there will be some missing data, or some data will not be counted. And we have to figure out all the, like, these are the main challenges which people face in real time during the forecasting on the ground. And one of our goals was to use statistical methods in order to alleviate some of these challenges. So we'll focus on the data quality issue, specifically data revision. So ideally, once we, for example, we get data for each week. For example, we get mobility for each week. We get the number of cases for each week, which are reported from different sources. But these values are not set. And for example, suppose, so this is for Texas, the mortality. So Texas public health authorities report like 223 death counts on week 28. But this value 223 will be revised as more and more uh, data becomes available, and there is more coordination among reporting. And over the course of time, this value will change to maybe, in this case, it changed over 400. So the same value, the death count on the week 228, which was reported on week 228, was revised up to almost 400 in week 30. So we cannot anticipate this change when we are forecasting using the data in week 220 on week 228. So this is a major problem which real-time forecasters face. So and also these data revisions are not sparse; they are very significant. We found that over half the signals show this error, the difference between the related difference between initial and final reporting values, over 32%. And the targets, which are the death counts, were also revised by over 5%. And the time it takes for the values to stabilize from the initial reporting to final value, which is the actual value, is up to 3 to 4 weeks. And this is significant because the model performance is affected by it. Like, usually people use data which is available at a given current week in order to predict for the future. But if you use this data which is which will get revised later on. So this is not the actual ground truth data. So the model will learn to predict the target, which is based on the data which is not revised. And this target will be different from the target which will be finally the final revised target, which the health authorities will report maybe after 3 to 4 weeks or maybe on beyond. So this is not same. So the entire modeling and training procedure will be impacted by it significantly. So our idea is to basically refine to automatically observe these revision patterns and refine these predictions in order to get closer to the stable targets rather than the initial targets which the authorities report in the current week. So formally, what we do is we look at all the revision patterns of all the features that has taken place in the previous weeks, and we look and then we look at the current prediction which any general model gives, and then we leverage these revision patterns in order to refine the current model's prediction to be closer to the ground truth. And that's basically our model called Back to Future, which does this automatically. So it takes it looks at the backfill sequences, that is the pattern of how the signals have been revised over time. And then it also looks at how the model has been predicting for the past few weeks. And then it leverages backfill sequences using a graph convolution network, which is a neural network that can be used on relational data. And we also look at, then we combine the knowledge from the past predictions as well as the backfill sequences in order to refine the model's current prediction. And this is basically the general idea. And the result of this approach, which is a purely statistical automatic approach of refining predictions based on previous revision, yielded some considerable significant results. For example, we were able to improve the predictions of some of the top performing models in the COVID forecast hub. And like, for example, we were able to improve it by almost 6.65% over some of the top performing models. And for some of the US states, the improvement was over 10%, which is very significant. So the takeaway is that while data quality issues are very important for real-time forecasting, there has been, like, we are using statistical approaches to make this correction is feasible and is a very interesting problem to solve. Next, we will look at a demo. Basically, I'll go over how the Back to Future works, and like basically how. So basically, Back to Future can be used on any model. So we have improved the predictions on multiple COVID forecasting models. So I'll just take you through the pipeline of how you yourself can use this to improve the real-time forecasting of your models. So I'll shift my screen to another system. Okay, can you see the screen?
Yes.
Yes.
Okay. So the code is publicly available and it's on the slides. So if you clone the repository, basically there are a few steps which you have to, firstly, setting up is pretty simple. You just have to run a script which will use Anaconda to get all the main dependencies. Then the first step is, so we have this dataset called COVID-19 dataset, which contains like multiple features. So this is one example of the dataset which we have collected over, and we keep updating almost every week. So it has multiple features, including mobility, text, and number of cases, ICU, a lot of and from mobility from Google, Facebook, a lot of different sources. So this data set is also available in the repository in the COVID data folder. Then the first thing is basically to pre-process this data set, which we do using so we just basically run a pre-process script. The details are not important. Basically, we just select the few features which we have found out to be the most important, and so we basically run this script, and then once we run the script, we get the PKL files for all the backfill the values for all the features, not just for the current week, but the entire revision of all the values over the past few weeks. And then once we do that, we train the model. The model training is done in 2 steps. First, we do pre-training. Pre-training means basically we just use the backfill values in order to learn embedding, in order to learn a model that embeds the backfill, the revision patterns efficiently. And this doesn't require you to provide the model predictions yet, your model predictions yet. So once you do that, you get that pre-trained backfill sequences in these. For example, for week 40, have these PTH files which contain the backfill sequences, and then you can basically have a CSV file which contains your previous model prediction. For example, for ensemble, this is the file, which is CSV file, which contains the epi week, the region, the target, and the value. The target is like 2, 3, 4 weeks ahead, and then initially it's 0, but later you get some values. And then then basically pre-process this to get the PKL values, and then now you have the pre-trained back to future model and your model predictions, and then finally you train the model for the current week, and then once you train the model for the current week, the output will basically be a dictionary like this for different regions. This is the initial forecast, and this is the refined forecast, and you can see that there is differences. Specifically, the model here in this case, it's saying that the revision will be to increase the mostly increase the values, the target values. So the back to future will basically give you the refined forecast. So the idea is that you can use your own model, create a CSV file, and then run the pre-trained back to future in order to get a refined prediction for your model. So that's basically the main takeaway of this. And I encourage all of you to, if you're doing any forecasting, go ahead and use our repository and see how it improves your forecast. So yeah,
I just want to add maybe that the link to the repository is on the chat, and also there are some instructions that Harsha has just commented. Yeah, just to add that. Harsha, please continue.
Okay. Then next we look at the other phase, which is the decision making part of the pipeline. So the idea is to leverage the model predictions in order to provide decision making in different spheres of life, like public health, policy making, and also if you're a business, for supply chains and stuff like that. Usually, a decision making lies under two different kinds of decision making, which is strategic and tactical. Strategic is more broad scale and more, like you can say, vague or vague. For example, whether you want to lock down a specific county or not. It's usually in that sense. Tactical is basically you have a end goal, but you have to optimize for it using some like choosing the right action. Like for example, if you have uh, like what's the best way to like distribute masks in your neighborhood? Like where should you keep the mask counters or something like that? So that is a tactical decision making challenge. So you leverage the model prediction in order to like predict what's going to happen in the future, and then you make decisions based on what the models forecast. That's basically the whole idea. So I'll talk about the one example of strategic and one example of tactical intervention. So for strategic intervention, there was a series of works by Probert et al., which does interventions for foot and mouth disease, which affects cattle and is a very serious problem in UK. So the goal is to like stop the outbreaks, but there are like multiple measures you can make, you can provide. One is to vaccinate the animals, another is to like cull the animals in order to like stop the spread to surrounding farms. And different, like each of these control measures have different uh, uh, trade-offs. Like vaccination may be ideal if you don't want to lose many animals, but it's also costly and slow. Culling is probably a little bit faster, but of course you are going to like kill cattle, so that's not ideal. So in one of their papers, they used reinforcement learning, which basically is like sequential decision making. Basically do an action, which is basically either vaccinate or cull some subset of the farm, look at the result, and then do another action. So it's a sequential decision making process, and people have used a paradigm of learning called reinforcement learning in order to solve this problem. And an example of tactical intervention is ventilator allocation. So during the pandemic, one of the like since it's a respiratory disease, ventilator availability is one of the major challenges in a lot of places. So it's a supply chain problem, and you leverage the model's forecast of how many cases we expect in the future to like optimize where to send ventilators. Again, there are trade-offs. You have to make sure that the number of ventilators available at any given county should be greater than or equal to the demand, the future demand for that. But also you need to reduce the transportation cost of ventilators from like manufacturers in one place or other. So they used another optimization problem. That's another optimization problem that they solved. Again, the important thing is they used the model's future forecast in order to prepare themselves for this for the resource allocation. So that's where there is this pipeline of forecasting and then decision making. Okay, I guess Alex will take over from here, unless you have any doubts.
Natasha, may I share my screen, please?
Okay.
Yeah. Okay. Yeah. Yeah. To finalize our presentation, we have already covered the main topics that we wanted to cover. We want to give some final remarks. The first thing, to restate that all models are useful. In this workshop, we have provided a toolkit of models. And as I emphasized before, ensembles are often the most robust. Mechanistic models often offer better quantitative insights, greater than qualitative accuracy, especially the engine-based models. And statistical models, they have usually state-of-the-art performance in multiple short-term forecasting tasks. And these hybrid models, which are gaining traction, are very interesting, and I think it's going to be it is already an active research area. Other questions that maybe going deeper into epidemics and data science is asking when, where, and who got infected. For example, when and where the outbreak started. And this requires accurately and timely data from the ground. And this is a very challenging question even for our capabilities to understand when, for example, this question of when and where the coronavirus started. Also, other question related is what and when, what to expect when as it is spreading, and what kind of people are likely to get infected, when this epidemic is going to peak. So many of these outbreaks appear and then die on their own. So can we get a sense of what are the characteristics of this? You know, one proxy metric that we use is the R naught, but it is very challenging to calculate. Also, another thing that we have to consider is that we need to data in order to understand how the disease will spread. And the role of these models are going to be short-term predictions, long-term predictions, understanding. And there are some conflicting goals, maybe accuracy. It is, you have to compromise on transparency in order to get more accuracy, as for example, in neural models, but or flexibility. There are some competing goals or conflicting goals that we are dealing when we are developing these models. And but the overall objective is important that we do this because we need to inform the resource planning and decision making, and have to move towards more answers that they are towards questions that usually decision makers have, like how big the peak will be for epidemic. For COVID, this has been very challenging. When it will peak, inform this so that we can improve communication to public, and the public can take also their own decisions. And for this, we require a combination of data, models, efficient algorithms, and simulations. In real time, studying in real time, the authors of this has been studied a paper 10 years ago, but it is still, we can still get some ideas from here that are valid for today's scenarios. We have to understand what are the risks for the pandemics, maybe understand which are the vulnerable populations, available interventions, implementation, what are the possible implementation policies that we can implement, and understand how to better make the public to understand the risk, and how to better prepare for this. So there are several processes that we can make before and after and during the pandemic. Before, we can determine medical interventions required, how to make feasible the containment, how to allocate resources or save some resources in case that something like a pandemic happens again. After the pandemic, we can quantify transmission parameters, interpret real-time epidemiological trends, measure what is going to be the shifts in the antigen, the dynamics, maybe as you may be familiar with the variants and so on. Assessing the impact of interventions is also an open question. And data science is very important for all of these topics. In addition to the increasing data collection that we have for this domain, questions about the epidemic spread have a large spatial and temporal scale. There are multiples of the scales, and the data that comes from these scales, either small or big, are usually noisy and incomplete. So there are some need for statistical corrections, like for example, harsher percentage. And we have found news. So we are developing basically new tools to help epidemiologists to complement their models, to provide different perspectives. And these new data science and AI techniques, have been a very active research area in the last few years. There are many breakthroughs, and we can leverage them. We can leverage also new stochastic optimization techniques. So this makes us form or set up a new field of a research area, that is data science for epidemiology, in which we are combining theory and algorithms, computational systems, machine learning, and statistics, along with biology, physics, social science, and economics. So I wanted to leave you with this idea of this emerging field. We have focused today in forecasting, but there are other multiple areas where data science can help epidemiology. I just want you to remind you of the workshop website. We are going to post the slides and videos there. We want to also let you know that I'll remind you that our survey paper is coming. Many of this presentation has been based on that survey paper. And we usually organize this epidemiology data science workshop. If you're interested, please stay tuned to the updates on the website. And we will also be posting more of our research and tools that we will be developing this year and also the rest of this year and next year. So we also want to share that we recently organized National Prevent Symposium. It was early this year. It was requested to us by NSF, and it was a very interesting symposium with very insightful discussions from experts on this area. And you can see the videos and hangouts are available. They are freely available, so you can please go. I invite you to go to the website preventsymposium.org and please take advantage of this material. I want to thank you for your attention. Thanks to the Forecasting for Social Good group for inviting us. Also the CDC COVID Forecasting Hub, data collection volunteers, collaborators, and funding agencies. Here is our information. I'm going to post we have a small survey that we will appreciate if you could fill up. It's just it should take you 1 or 2 minutes to fill. The link is there. I'm going to also post it on the chat. So I just posted on the chat. If it would be great if you could please give us some feedback on what can be improved, what we did well. So yeah, thank you so much. Please stay tuned. So Ming, thank you. Baman, thank you so much. Thank you for the invitation.
Hi everyone. Hi Alex. Sorry, I'm actually in France, and today I had teaching as well from 8 in the morning, and I finished just at 4 o'clock, and that's why I couldn't attend. But thank you very much for that, Alex and Harsha. And yeah, so if I think most of people, I don't know how many attendees actually you had the whole day, but I think many people, they were maybe interested in getting the recording as well. So we are going to put the recording later on in the website, but also the materials that you shared, we put in the website as well. And then we send an email to all potential participants registered for the workshop as well. But we do a couple of, different initiatives in forecasting for social good. So if you are interested here to contribute and you have time, so I think we need really support and help. So feel free to get in touch. That's, I think, one thing. I had another thing. Yeah, can I ask 2 questions related to the COVID and pandemics in general, or maybe you have
for sure.
We have covered things before. All right. So, 2 questions I had is, the first question is more related to the sort of research we do in pandemic and in particular in COVID. Majority of this research is in the like global or national levels, but in reality, many local authorities, they need to make decisions as well. But then there is a sort of like challenge dealing with that kind of thing, because regardless of what you're looking at, hospital admissions, number of cases, number of deaths, etc., it is likely that the time series becomes a bit more challenging. You're getting many zeros, for example, in some days you don't have any numbers, and then sometimes you see a peak as well. So I was wondering whether the sort of models you considered or you reviewed or you have seen, they are applicable regardless of the level that you we consider. So it could be, as I said, a county level, for example, really a level where you manage one hospital or 2-3 hospitals.
Yeah, that's a great question. Actually, that is an active research area. We have seen that we can use the models as they are because the dynamics of the disease spread are usually the same, and as long as we have data available, we can use them. But they have difficulties, as you mentioned. There are some zeros, there are some spikes. So the data at very localized levels has some even more data quality issues. So what we have been exploring is maybe taking advantage of the hierarchical structure. So if we have aggregated data at one level and we have a more robust model, can we use this model to maybe help the other more granular models to learn better, to be more stable to these spikes or the quality issues, right? So we are also, this is an active research area. Is I think this is the next one of the next steps to move forward this field, because we actually want to provide localized localized predictions for decision making, and also for even individuals, right? Individuals are interested of learning about what decisions they want to make, and this is requested. So Harsha, do you want to add something? Not sure.
No, like I think Alex has covered everything. Yeah, there are like interesting problems, at least in local level. I think IT has done some work with regard to like hospital allocation and dynamics of inspection in hospitals, and I think those have like different dynamics, and like we can use more mechanistic approaches also for those
All right. Yeah. Thank
low
you.
level things.
Well, the
Yeah.
next question I had is more related to, you know, the time, because the pandemic evolves over time, and so we get really different useful information at different point of time. So for example, in the beginning of pandemics, maybe I mean in this COVID-19 in particular, when we started, so some sort of data like Google Trend, like phone calls, right? For example, in the UK, NHS 111, which was dedicated to COVID. So that sort of data could be really, really helpful to get the number of hospital admission, number of COVID cases, etc. But if you look at it like further down, and I mean closer to now, actually that data becomes less important, and some other new data becomes more important. Like, you know, we have as we evolved over time, we got more data related to, let's say, number of people tested, and that was maybe an interesting variable. And then we got, of course, the mobility data as well from Google, Apple, from Facebook, all these organizations. But I mean, more recently, we got also the percentage of people vaccinated, the first dose, second dose, maybe third dose, all the things. So the question is, does really one single model works overall? You know, you just have a model and then you take variables, etc. Or these models need to be updated, or maybe different variables should be used for different part of pandemic and not for the others. And what do you think about that?
Yeah, this is a very, very important question. First of all, I think we think that, and also we want to convey that many models is better, usually, because not a single model can capture all the things that are happening on the ground. With respect to understanding what to use at each stage of the pandemic, yeah, there are some techniques that we can exploit. For example, we have presented in one of the slides that we were trying to understand what were the most important factors for our predictions. So that is kind of a technique that we can use also for understanding what is the most important set of features, of feature selection, basically understanding what is the feature selection that has to be used, and it's going to be evolving. all of the time, right? It's what we have to be updating. So this is because it's a very dynamic and chaotic scenario, still a bit chaotic. So things can happen. Maybe in 1 week we are going to have another closures again. So the things are change very fast. So we have to update our models. We usually what we do is train our models every week, and that is usually what gives us the best performance that we have gotten so far. Yeah. Kasia, do you want to add something?
No, yeah, just like it's not clear how much engineering effort is required because we can't like measure it, and I think that's one of the things why we have to standardize all these things. And yeah, it's still a very open challenge. It's different from like normal NLP or computer vision kind of stuff, and it requires some of this. Yeah.
I want to add maybe something that statistical methods allow us to open a door here to understand what is the importance of these indicator signals over time, right? So there are some mechanisms that can allow us to downweight some of the signals that are not very useful, or increase the importance of other signals that maybe depending on the epidemic stage. So those are interesting areas that we can explore with these statistical models. The maybe mechanistic models is more, you have to do more engineering, right? More crafting. But statistical models can do it automatically. So this is an interesting thing that it can be explored.
Yeah, thank you very much.
Great. Thank you, Alexander and Harsha. Thank you for your wonderful meeting. And also thank you for others for attending this workshop. And if anyone have another question, you can ask now. And if not, I can stop recording now.
This is Mohammed from Rwanda. Thank you for the good presentation. I saw that you advised that for the robusting model, using the median, it's more better compare on using the mean. But my question was, that also has influence depending on the outcome that you have. Some of outcome might be much appropriate of taking into consideration model mean instead of median. So what is your say about that?
Yeah, I agree with you. It depends on what are the outcomes, what are the targets that you're predicting, and what are the models that you're using. So in this experience of a specific experience of COVID forecasting hub in the US, there were some models that were over predicting very largely sometimes, and as I mentioned, they were driving the mean towards undesirable regions. Therefore, what they decided is, let's take the median among all of the models, right? It's kind of the consensus of across all the models, and that is going to be the prediction. And that resulted for this specific case, resulted the most robust prediction. But for example, if we look at influenza forecasting, where you may not have this behavior of models that are over predicting, maybe the mean is the most appropriate. Maybe I think that there is one paper that also we cited is from Professor Nick Reich in PNAS. It is that they are studying ensembles for influenza forecasting, and maybe I am almost sure that they also have one ensemble that is using the mean. So maybe you can explore that, but it depends. Yeah, I agree with you.
Okay, thank you.
Okay, so if there are any other questions,